So I will talk about Diapason. Diapason is a set of tools and technology we develop at CEA for dealing with the development of CPS, Cyber-Physical Systems. So I am Sébastien Gérard, working at the CEA. So what is first the CEA? CEA means for French institution for working on atomic energy. It's a research institution. It's about 17,000 people, located mainly in France, in different centers. There are mainly 4 divisions. One which is historically working on defense and security. It was the purpose of the creation of the CEA just after the Second World War. Then we have a division focused on nuclear energy. A division focused on fundamental research, working on different areas like life science, physical science, and so on. And the one where I am working, which is called CEA Tech, which is focused on any kind of technology for all industry which are not defense and which are not working on nuclear energy. So within this division, we are 6,000 people working mainly in three parts of the France, in Sèvres-Saclay, which is south of Paris, in Grenoble, and in Chambéry. Within this context, within this division, there is the labs I'm leading, which is called LASE for Laboratory and Model-Based Engineering for Cyber-Physical Systems. It's about 44, 45 persons, mid of full-time researcher and mid of PhD, postdoc position, and so on. We are working very closely with the industry. Our main activity is to transfer research to the industry, so we are very close to real needs from industry. We have partnerships with industry like STL, Sherpa, Ericsson, and so on. And we are very involved in standardization. So in international standardization, we are involved in OMG and AUTOSAR. OMG is for Object Management Group. This is the international organization. Standardization for UML, SysML, and AUTOSAR is a European organization standardizing language and infrastructure for the automotive industry. So we are a research institution, so we are working on several areas. The labs is very involved in all these areas. So model language engineering. So we are working on how to design a new modeling language, how to implement tools which support new modeling language. Because we are involved in safe, I would say, CPS system, we are also very involved in formal analysis. Runtime verification, we also provide some features for model simulation. We are working on safety and security, working on exploration, architectural exploration, product line, code generation, trace model compilation, and so on. So we try to cover I would say, mainly the left branch of the usual B cycle with some activities on analysis for verification and formal verification and validation. So our domain of interest is, I would say, mainly the world, because we are working on embedded systems, this also called CPS, and those systems are everywhere. So they are in all the systems that we are using or that we are part of. And one of the main issues is that these systems are failing. So there is failure. A lot of these systems are using software. A lot of the features of this system is based on software, and a lot of the failure are coming from the software. So one of the purposes of my labs is to try not to find the error, but to avoid to have error when you design your system. So we can talk about correct by construction design. If we look at this, there is a lot of reports that state about why there are failures in the system and so on. So if you look at this report, there is a common conclusion that, as for example, one of the main issues is the inability for the project stakeholders to handle the complexity of the system development. And communication issues are also very important and very often the case for the failures, bad system requirement development, not enough usage of the possibility of the computer-aided design, lack of tools and techniques to manage and analyze the risk of the development, and of course the time to market pressure with in parallel the need to provide more and more qualified systems. So the problem is the complexity. So there is indeed two dimensions of the complexity we want to deal with. The first one is the increase of the complexity of the system to design themselves. So the system needs to provide more functions, to provide more added value to the users. So they need to also take into account more concern, like more function to deliver. And they are more and more in interaction together. So we are talking about Internet of Things. The reality is that all the systems are more and more in communication, and the frequency of the communication is also increasing. So the complexity is coming very often from this concept. Second dimension of the complexity is from the constraints themselves that has to be satisfied to develop a system. We have to do it quicker, but we have to satisfy more and more constraining standards, like for the automotive, like for example, there is a new safety standard ISO 26262, and almost all electronics design or electronics device now have to face or have to be conformant to a kind of safety standard. There is a lot of more and more pressure on that, and of course better quality and of course cheaper. So this is a cocktail of complexity which is very difficult to face and to deal with, and it is the context where we are working. The current approach of the design of the system is you set up a team of people. These people will have some responsibility, so some concern, like to deal with the risk analysis, to deal with the project management, to deal with the maintenance of the product, the development, and so on. And for doing that, they are going to exchange information, maybe formally by document or model also, but mainly, usually it's very informal. It's only discussion. It may be only discussion. It may be only email and so on. And this informal discussion may be a source of failure, very important source of failure. So this process becomes to be unreliable, inefficient, and not scalable, because the more the systems are complex, the more you find people involved on information. The size of the information exchange becomes very, very bigger, and in fact it becomes unmanageable for a human. So the idea of the model-based development approach is to try to Okay, so the idea behind the model-based development approach is to formalize the information anyway. So the idea is this concept of model is just a formalization, just a concept to formalize, in fact, the information which is exchanged by the people, and to formalize also the exchange of the information. So we formalize the relationship between the information, the model, and this relationship formalization is either a transformation, so you can produce, as for example, a specification document from a model of the architecture description, or it's also sometimes a trace relationship between two different models, where a model could be focused, as for example, on the control aspect of the system, and another model focused on the architecture description. So behind model-driven engineering, there is two main concepts that are very important to understand, which is abstraction and automation. So abstraction is what we put in the domain of modeling language engineering. So it is the art of designing the right model language for your problem, for your concern. So behind this concept, we often have this concept of domain-specific modeling language. And the automation. So there is two main principles. Is the ability to describe, to abstract a problem, and the ability to exploit the abstraction, the description. So model compilation is a kind of automation, code generation, documentation generation, and so on. And we put that in the context of the automation, we get this what we call computer-aided modeling, or expert system, in fact, behind that. An additional very important point for us, and I think that this point is becoming more and more pregnant for software developers, is that the software you are developing will have to be certified, or will have to be very safe, because the software will be embedded in a robot, as for example, but not a toy. A robot that provide help to the users, to humans. So you need some certification, or either you are going to use a car which will drive for you. The software needs to be certified. So there is a need to shift the way we develop software today, which are okay very often, but for this kind of system we cannot satisfy about, okay, it looks like to work. It has to work every time or under every condition. So there is concept of certification is behind that. And then usually the concept of formal modeling or formal design is needed to be able to achieve the certification. So to be able to switch the paradigm of the development, or to go from this red picture to this green picture, we promote, in fact, through four pillars, four main concept paradigm. So the first one, we promote to use model-driven paradigm. Then we foster to use standard. So it could be international standard like OMG standard, AutoSAR standard, but de facto standard like, for example, Modelica and so on. There is a very important focus on the architecture concern of an application, which is very important for us, and it has to drive the development. This is the architecture part. So what are how you cut your system in different parts, what are the dependency and the communication between each of these parts, and this concept of multi-modeling, because for sure, as I said, there is several people that will be involved in the design with several concerns, which is the base of the design. And then for these several concerns, they may use different language, different tools, and so on. And we need a mean to integrate all this language. So this is what we call multi-modeling. And for sure, it has also to be formalized. One of the language we are using, and one of the language we use in my labs, and we use as a, I would say, as a foundation, is the UML language, which is a unified modeling language. So it's a language that has been standardized 15 years ago, something like that, maybe more. It was the result of a lot of feedback and a lot of expertise from several people involved in methodology and design. And it's indeed, so maybe all of you know UML, it's indeed a set of language for different purpose, automata, interaction, and so on. And one of the usage of UML is also to be used as a pivot language between the different modeling aspects involved in the development. But for sure, UML is a generic language. It was designed for software at the early stage. And there is a mechanism inside UML that enables you to construct a specific language called the SML using UML profile. And using this concept of UML profile, you can either simplify UML. So a lot of people are claiming UML is very complex. Okay, you can cut and use the part you want, Or if you don't find what you want inside, you can also extend or specialize existing concepts. And one of the advantages to use UML is to reuse all the experience which are behind UML. So it's a lot of people who have been involved in that, and very smart people. So the idea is to reuse what exists. And if you don't find what you need inside UML, then you can do something very specific. But first you have to investigate UML. This is what we claim it is important. This is an extract of a presentation done by an Ericsson guys at the Models Conference. So the Models Conference is the most important conference in the context of model-driven engineering in the world. And this is a very good point to say that UML is not really the problem. The problem is the tool that implement UML. So, and one of the main issues is that people have decided to not to reject UML because of the tool that they have used, not because of UML itself, but because of the tool of UML. So, several years ago, we were also a user of UML before to be a developer of a UML tool. We decided to make a UML tool. So this is Papyrus, and so Papyrus is now provided leave the incubation this year in the concept of Eclipse. This is a tool for UML. It includes a very high support for profile definition, and it may be used either for people who make who want to make a R&D experiment in the context of model-driven engineering. It is a real use case with industrial constraints by itself. And it's part of an industrial activity we have at the CEA, and it's now a real Papyrus reached a real industrial level that is now used by several people for making real projects or for selling products. So it supports UML 2.5, the last version of the standard, SysML and MARTE, which are the main, the two main extensions of UML standardized by DUMJ. Sorry, the first one for system engineering and the second one for real-time embedded design. But it also provides support for defining domain-specific modeling language. So we use the profile concept, so you can define your own extension, but you can also customize every part of the tool. So either you can define your own editors here or customize the existing editor, as for example this one. You can have so first it was designed as a graphical language, but you can also use textual views of your model. So we use Xtext as, for example, for doing that inside Papyrus today. But you have also tabular view or tree-based view that are, all these views are extensible and are customizable within Papyrus. So you can choose to either show a plain UML model or a plain DSML-like model. It's up to you to decide and to put the cursor where you want. An example of DSL we have done is for the robotic system. So we have defined a language called RobotML, robot modeling language. We experiment now the language and the infrastructure with a company who is making this robot. I don't know if you know this robot, but it's a humanoid robot. It's Romeo. And this robot is going to be used for giving healthcare to people. So we are making the system description of the system of this robot, and we are making safety analysis using the model we have done, and using a tool I will show later to check that the system description is conformant to a given standard defined for robotic system. So this, I will make just a short video for the modeling side. So this is the Papyrus framework, so you can open a model. So this is an example of the Romeo model. We have used the DSL we have built for them. Within this example, there is a part for the hardware architecture and software architecture of the robot, and there is libraries of the part of the robot that has been defined with specific layout, and then based on this library of part of the robot, the user can describe the real robot, like he make an assembly of the element, describing every part of the robot statically, but also after we can describe the exchange, the various exchanges that exist between the different parts of the robot. So this is a plain UML view, and previously it was a DSL view of the language. So it's very important to be able to make model to describe, but it's also very important to be able to exploit the model, because sometimes the model has become very huge, very important, and we need to assist also the user to analyze the model. So the current situation is that once you are able to make a model, the model is used for some purpose, as for example to make an analysis, so it's safety analysis, a performance analysis, or risk analysis. Today it is based on human capacity to compute, I would say, the model and to extract the information. The idea is to put a formal tool in the loop to assist the user to analyze some part of the system and to transform this analysis into results that will help the user to analyze better the model themselves, and to be able to scale the problem, to be able to be more reliable with respect to their analysis, and to be able to decrease the level of expertise needed to perform this kind of analysis. Behind that, there is a need to be able formal. So a claim that we had in the context of the UML community, there is for a long time a claim that UML is bullshit, UML is non-formal, and so on, so on, so on. There is an activity that is started 5 years ago at the UNJ to formalize UML, and by formalizing I mean to put mathematical semantics behind UML. I do mean that. So there is a standard called FUML, Foundational UML, which is a subset of UML, mainly focused on class diagram and activity. So conceptually, it's like Java, I would say. You have all these concepts. And there is a mathematical foundation behind that part of UML. There was also a work to provide a new version of UML, which is not really formalized, but which has been very, very well redesigned in order to reduce as much as possible ambiguity in the description and so on. And based on this first work, Foundational UML, it's a kind of iterative works where the other part of UML, so as for example the state machine, the interaction, and so on, will be formalized on top of this first layer, I would say. So the first layer, the second layer that has been formalized is called PCSS, for Precise Semantics of UML Composite Structure, and it's in fact it's fit with in the context of UML. It fits to the concept of component, port, and connector. So it is the part of UML which is dedicated to architecture description language. So within this context and with this all this part, we have developed a framework, a workbench called Diapason, which purpose is to take into account all these concerns. So for safety, security, we have developed a framework called Sophia. We'll come back later on that. We have also developed a framework called Compass to enable what we call analysis-driven architecture. So it is where we make some optimization of the deployment of an application, schedulability analysis. We have developed an extension focused on requirement engineering, one focused on formal analysis, one focused on model-based simulation. I will make a snapshot on this one also. One dedicated to provide support for monitoring application, as for example if you need to make diagnostic.
Try this one.
Yes. before interruption.